Hey everyone, it's Vian from LearnML. Today we're going to go and deep dive into deep learning. I'm going to try break down the entire field of deep learning, or just the basics of the field of deep learning, and especially focus on the practical side. And given your application that you're trying to build a model for, what are the best parameters to start with, the initialisation techniques, and the architecture of your neural network. We're going to cover all of this in depth. Plenty of examples, so feel free to follow along. There's a Colab notebook in the description. And so yeah, let's get started. So after this course, you're going to be able to build a neural network for any application. We're not going to be talking about recurrent neural networks or computer vision based neural networks, but in most cases, if you're doing classification or regression, then the neural networks we're going to be covering will be suitable, and it will give you a good basis for learning the more complicated or more specific neural networks for the future. I'm going to skim over a lot of things and a lot of the mathematical details in interest of time, because of course I'm trying to cover the entire field in 1 hour here. So in terms of prerequisites, we assume that you already know how to code in Python, and that's going to be useful if you're following along, of course, but also some basic knowledge of the libraries, the scientific libraries such as NumPy, Pandas, and Matplotlib. And that's basically it. Just some high school maths is also fine. And also an interest in machine learning. So you should know some of the basic terms such as an error function, perhaps even gradient descent. You should know what I mean when I say classification or regression, and normalization, just some of these basic terms. Okay, so here's a roadmap for this video. So in part 1, we're sort of going to focus on the motivation and the key components of deep learning, and we're going to start with the biological motivation. Then we're going to, in part 2, focus on how to actually build these things using TensorFlow. And in part 3, we're going to focus on how to actually improve on our results that we've already scored in part 2. This is a great textbook. I recommend you pick it up. I have loosely based this course on the contents of this textbook, because I think it's really useful for if you're taking an online course or something, to have a textbook to refer to. And so this is a great textbook as well. So yeah, it's very new. I think it came out like 6 months ago or so. So I really recommend you pick it up. Okay, let's get straight into it. Here are the recommended readings if you are going to be going more in depth. Okay, so why neural networks? Let's start with the biological motivation. So throughout history, science has looked at nature for inspiration, but often you'll see that the paths that science takes ultimately diverges from nature a lot of the time. So sometimes it's an exact replica like Velcro, but sometimes, if you think of the case of flight, first humans started trying to build these flying machines that replicated birds, like sort of the Da Vinci era. But now, of course, we have planes that are similar to birds, like we have wings on planes, but ultimately it took a different direction. And this is sort of similar with artificial neurons. So the ground motivation was to replicate a neuron, but there's a lot of differences, and it's unfair on the neurologist to say that an artificial neuron is just like a neuron. They're pretty different, quite different in fact. Okay, so some successes of deep learning. Top left, we see translating or transforming black and white images back into colored images. This has some cool applications when you're trying to restore very old footage. There's a YouTube channel that does this, I think, where they take footage from the 1900s and restore it with full color. and some of the other applications I'll just quickly mention. So here is some computer vision being combined with natural language processing, and what's happening is the model is describing what's happening in the photo, which is pretty advanced if you think about the number of computations going there. Okay, this is a biological neuron. This is not a biology course, so I'm going to skim this. But the main components, cell body, axon, and the axon splits up into the synaptic terminals. And this is attached to the cell body and the dendrites of another cell. And a cell essentially, a cell essentially just fires these, the neuron fires a lot of these electrical impulses, which go through the synaptic terminals. And if a neuron is having a lot of these electrical impulses going into it, then within a given period of time, it will fire its own electric signal. Okay, so that's oversimplification. These neurons are actually incredibly complicated and still not fully understood. Some parts of the human brain have been mapped out, as you can see in here. Okay, throughout this course, there's going to be a lot of these mini quiz questions that sort of ask a question based on the material we've just gone over. Feel free to pause the video every time this happens and try to answer it yourself. So here's an opportunity to do that. Okay, so let's construct a single artificial neuron. So using the analogy of the biological neuron, let me see if I can just pull up. Okay, so we have these inputs coming in. We denote inputs as X, and each input is multiplied by a weight vector W. And so essentially what we have here is we have the inputs coming in multiplied by some weight parameters. This ultimately gets summed, so it's just a weighted sum. Then we add a bias term. A bias term is just like an intercept, and you can see this sort of resembles a linear regression, and that's exactly what it is actually. And after this linear regression, then we apply a nonlinear activation function. We'll talk about why they're nonlinear later. But okay, a neuron in a nutshell, or an artificial neuron in a nutshell, is simply a weighted sum of the inputs with a nonlinear activation function applied to it. So it takes in a vector of inputs and it spits out a scalar. All right, so I've just talked about this, so I can skip over that. Okay, mathematically, it's nice to represent inputs as vectors or matrices if you consider all the inputs, because this is computationally efficient and easy to denote. So we'll go a little bit over that soon, actually. Okay, so here's an opportunity to pause and answer yourself. And there's the answer. Another question. There's another answer. Okay, so let's go and actually review what we've just learned about a single neuron. So when I talked about the activation functions, here is one. It's called the sigmoid activation function. And here is the code for it written as a function. So a neuron, we're just going to ignore the bias term for now. So we're just going to do the weighted sum. So we pass in an input vector X, or we pass in the input vector, then we denote it X for consistency. We randomly initialize the weights for the weighted sum. This is important because otherwise all your neurons are going to do exactly the same thing. So we randomly initialize the weights, and then this Z is this weighted sum. So we're doing the dot product between the weights and the inputs, which is just a weighted sum. And then here we're applying this nonlinear activation function. So this is just a function of a neuron. If we pass in a vector of 100 ones, and then output this result and then store it in a list 1,000 times, then we get something like this. So you can see we have a lot of saturation at 1 and 0. That's because the sigmoid activation function this is a characteristic of the sigmoid activation function. This activation function is essentially some kind of pseudo probability mapping, mapping from the real axis to any number between 0 and 1. So here I've plotted it, but you can see that as numbers become large or very small, it will either plot or map to 1 or 0, and this is actually a problem, not because of the 1 and 0 mapping, but if you look at the gradients, the gradients tend to 1 at both extremes, and this can make learning difficult. We'll talk a little bit about that later on in the last part of the course. Okay. So we've talked about a single neuron. We've seen how they are computed. Now let's look at how we link these things together to make a multi-layer neural net. Okay, so here's one of the neurons that we were just looking at, and here are all the inputs going into this neuron. This neuron remembers doing a weighted sum, applying a nonlinear activation function, and spitting out a number. So here's that number coming out. Okay. Now if we add another neuron in the same layer, then this neuron and this neuron, they're doing exactly the same computation. The only difference is that the weights, because they're randomly initialized in each, the weighted sum will be slightly different. Now if we add, let's say, K1 of these neurons in this layer, then each one of these neurons is fully connected with all of the inputs. Okay, so they're all doing a weighted sum and spitting out a number. Now if we add another layer, and here is another neuron. This neuron is also connected to all the previous neurons, but not connected directly to the inputs. So here's the weighted sum of the inputs, and the output is connected straight into this neuron. And each one of these neurons is connected to this neuron. And so this neuron is doing a weighted sum of the previous neurons as outputs. And similarly with this one. Okay, so you can add as many layers and as many neurons per layer as you would like. Of course, computation cost increases as you do this. But the more neurons, the more layers you add, the more complicated of a function a neural network can learn. And one extremely important thing to know is neural networks are actually universal function approximators, meaning that they can approximate any function, which is obviously a great characteristic and a great property to have. Also, another thing to note is the no free lunch theorem, and this essentially says that there is no one neural network or no one model that works best for all applications. Okay. Okay, before we talk about Backprop, let's have a look at this in action. Okay, you can read through this more in your own time, but what we're going to do is we're going to create a mini neural network that we can do a forward pass on. Okay, so let's say we have this input layer. So this is just a vector of a single input. Then what we do is we create 4 neurons here. And this is like the first hidden layer. So hidden layer is called a hidden layer because we don't directly observe it. It's not like the input here where we're passing the data in. So we have 4 of these neurons. So each neuron does a weighted sum of this input, and because each neuron is randomly initialized, the outputs are going to be different. So we store the outputs here, 4 outputs. We stack the outputs into another vector, and we call this H1 out, or hidden layer 1 out, and this is the output. Now if we feed this output into another neuron, just notice a small mistake. This should be neuron B, because here we're actually adding a bias. Then when we perform this weighted sum, then we get a single number. And this is the final output of the model. So we've got 4 neurons, then 1 neuron. So if we go back a slide, it's like having 4 neurons here, so ignoring these, having these 4 neurons and then outputting 1 neuron. And here I just talk a little bit about the matrix notation. You can pause and read in your own time if you would like. Okay, backprop. I just want to capture the intuition here, and I don't want to go too deep into it. We're going to be looking to release a more extended discussion on the mathematics behind neural networks. So if you're interested in that, then that's something to look forward to. All right. So backpropagation. Okay, so we've got these errors that when our model predicts incorrectly. And so if we plot the error against the weights or the parameters of our model, we can have some sort of curve like this. In reality, it's going to be much more messy. And in reality, you're not just going to have one weight parameter, but you're going to have thousands of dimensions and perhaps even millions. So before we get too deep into that, what you're trying to do is you're trying to minimize the error. And so you're trying to find the optimum weight to minimize the error. And so in an ideal world, all that you would do is you would take the first order conditions and you would find the minimum. Now, the problem with neural networks is that there's no analytical solution. So there's no formula to work it out in one shot. But you have to perform numeric approximations. And so the main algorithm is called gradient descent. And you can see why it's called gradient descent, right? Because we're trying to descend the gradient of this error surface to find the optimum weights. Here, if we have 2 weight parameters, then it's more of like a bowl shape. Okay. So what happens when a neural network is learning is it does a forward pass where it's doing these weighted sums and outputting a number, and then using the loss function, we then differentiate each one of the parameters with respect to the loss function and seeing how each of the weights or parameters contribute to the error. And doing this, we can then update the parameters by moving slightly towards this minimum. So for example, let's say that we evaluate and we see the error is at number 3. Then what we can do is we can increase the weights a little bit because we will see that there is a negative gradient. And so if there's a negative gradient, then we need to increase the weight a little bit. So let's say we go here, and again, there's a negative gradient at this point, so we go a little bit more. Let's say we overshoot and we go here. Now we've got a positive gradient. So now we need to subtract the weight a little bit, and then eventually we converge. This is called optimization. We talk about this, or the optimizers we'll talk about later. Right. I think I've covered that, so let's not go too much into that. Okay, here's another quiz. Pause and answer in your own time. So I've mentioned that a model is able to learn more complex functions when you add more hidden layers and also more neurons per layer. Okay, so why are activation functions nonlinear? So if you consider f as the activation function, g here is just, you can see a linear function, right? This is just a linear function. And so if we pass this into f, what's the output? Well, it's another linear function. What does all of this mean? Well, it's saying that if you have a linear function and you put another linear function into that, well, you're just going to get another linear function like this. So there's no increase in complexity, so you can't learn more complicated models. Or you can't learn more complicated functions, I should say. So having nonlinear functions allows us to learn more complicated functions. Okay, so here's the sigmoid activation function. We've touched on that in the workbook. The ReLU is a super important one and one to know. It's just the max between 0 and z. So if you have a negative number as z, you just output 0, and if it's positive, you output z. Tanh is another one, and you can see it's related to the sigmoid function in some way. Okay, so if I go back a little bit, for each one of these hidden neurons here, you can apply any one of these activation functions or any proper activation function. However, when you're outputting, you want to use a special activation function that's going to be suited for the task. So let's skip forward a bit. Okay, so if you're doing binary classification, then you want to use the logistic activation. For multi-class, you use softmax. Softmax ensures that all the class probabilities sum to 1. For regression, this depends. So none if the outputs are unbounded, ReLU for positive outputs, and Tanh for bounded. And we also use different loss functions for different models. So cross entropy is used for multi-class and binary classification. And for regression, we use mean squared error. If you're interested in cross entropy, there's a video where we derive the maximum likelihood estimator for the Tobbits model. And yeah, if you're interested, I'd recommend you have a look at that video. This is the sort of cross entropy formula that you may be familiar with. Okay, and again, pause and answer in your own time. Okay, so let's see what there is to do here. Okay, let's touch on activation functions. So here's the ReLU that I've mentioned. We're going to be using np.maximum. This computes the element-wise maximum of the two arrays that you pass in. So if we pass in 2, 2, minus 10, and comparing this to a stack of zeros or vector of zeros, then we get 2, 0, 0. Why? Well, because minus 2 and minus 10 are negative. If we change this to a positive 2, then what do you think the output would be? That's right, 2, 2, 0. Okay, so here's the ReLU activation function written in a Python function. Okay, now if we generate this x using the numpy's linspace function, what we're doing is we're generating an array of numbers starting from minus 10 to going to 10 with 50 points in between. So if I explain that badly, then this is what it looks like. So minus 10, and then there's 50 of these points going all the way to 10. Okay, if we plot this on a line, as you expect. Now let's pass this into our ReLU function. And that will sort of show you what the ReLU function looks like. Also, just one quick tip. Sometimes you'll notice if you do plt.plots, you'll have this annoying thing. One way to get rid of it is by doing plot.show. As you can see, it goes. But another cool way is simply just to add a semicolon. Same result. Okay. So, if you'd like to just have a read of the summary, that's just probably not a bad idea, but I'm just going to move on. Okay, neural networks for classification. So in this part, we're actually just going to cover how to build neural networks using Keras, which is built on top of TensorFlow. We'll talk more about that. So after this section, you'll be able to know how to build a neural network. It's quite exciting. So in just maybe, I don't know, 20 minutes or 15 minutes, you'll know how to build a neural network. Here are the readings if you're interested. All right, so we touched on which activation functions to use. So I can skip over this. Okay, what is Keras? Keras is a high-level deep learning API. And so TensorFlow, you've probably heard of this if you've been in the machine learning space, but it was developed by Google, and it's basically an extremely good package for training and building deep learning models. And Keras now comes bundled with TensorFlow, or TensorFlow comes bundled with Keras, I should say. and you can access it with tf.keras. We're going to be using Google Colab a lot. I really recommend that you get familiar with it if you haven't heard or don't know about Google Colab. It's essentially a Jupyter notebook on the cloud, and you can run everything on Google's servers, including free GPUs or TPUs, and everything's completely free. It's not like a free trial. All that you need is a standard Google account, and you can just run Google Colab files. I use it for most of my work just because it's super easy and you can share it. Yeah, really awesome stuff by Google there. Okay, so quick quiz. What's the loss function for binary classification? And yes, it's the binary cross entropy, sort of gives it away. Okay, how to create a model in Keras. So the neural networks we've been looking at are sequential, right? Because we have an input layer, then we have a hidden layer, then maybe another hidden layer, etc., and then the output layer. So it's sequential because the information is being passed forward sequentially. And these layers that I've just talked about, these are dense layers because they're fully connected. That's all dense means. That's the note, or the what they use in Keras and in TensorFlow. Let's also import activation and input layer. Input layer is just a special layer to note that, okay, this is actually the input. This isn't a hidden layer. So we start by specifying the model as model equals sequential, and then we pass in some things to this sequential function. And what we do is we pass in the input layer, then we pass in whatever layer we want next. Okay, so let's say we want a hidden layer with 64 neurons and the ReLU activation function applied to each neuron. And then we add another layer, 64 neurons, same activation function. And then we have the output layer. So we don't have to specifically say that this is an output layer. We just have it as the last layer, and we have 3 neurons, and we're applying the softmax. Can you remember what task this would be? So remember that we have 3 output neurons and the softmax. So hopefully you got that right. So that means we are doing multi-class classification with 3 classes. Softmax, remember, is also like a pseudo probability function that ensures that your inputs, or sorry, the outputs are going to sum to 1. And that's a desirable property because if you predict an image, for example, as a cat or a dog or a frog, you want to make sure that the probabilities are going to sum to 1 in the output. Because otherwise you could predict like the probability of a frog is 2, and that doesn't make sense. Okay, here's another way to specify a model. I prefer the first version, and I recommend you use the first version also. There's some reasons for that, which I'm not going to go into. Okay, here I just explain what I just explained, so let's skip ahead. So we've specified the model architecture. What we want to do now is we want to compile the model, and that means associating an optimizer and a loss function with it, and also some metrics to track how it trains. And this is how we do it. We've done model equals sequential blah blah blah, specified it. Now we do model.compile, and you don't have to save anything to this, or you don't have to assign a variable to this model.compile, because model is simply like an object. Think of it in object-oriented programming. You have an object. Now we're changing the state of this object by associating these this loss and this optimizer and these metrics. So we do model.compile, specify the loss and the optimizer, categorical cross entropy. This means that we're doing multi-class classification, and we have categorical, meaning that we're going to one-hot encode the output vectors. We'll see what that means soon. Optimizer, RMS prop, we'll talk a lot about optimizer soon. Metrics, we're going to track the accuracy. Okay, training, and this is also very simple. We just do model.fit, but this time we assign it to a variable called history so that we can see how the model trains over time, and then we can evaluate and plot like an error curve over epochs. Epochs are just the number of training cycles, you can think of it as. We pass in the X data, meaning the input data, and then we pass in the output data. And we just want to find a function mapping this input data to this output data. Validation data, if you know basic machine learning things, then you'll know what validation means. If not, Google it. Okay, error curves. This is how you plot an error curve. So we'll also look at why this makes sense, but in this history object, you can access the history, which is just a dictionary of each of the metrics that you specified. So we specified accuracy and the associated accuracy over the epochs. That will make more sense in a second. Actually, maybe I'll just look at it right away. Actually, I can't because I need to train the model, so we'll have to come to that. Okay, let's say we want to evaluate the model. This means using the metrics we specified. How well does our model do on these metrics? Okay, X test, Y test, these should be out of sample, of course. You don't want your model to train on the data and then you test the model on that data. Doesn't make sense. Okay, if you want to predict completely new predictions, then pass in X new, for example, and we use the model to predict, just model.predict, very simple. Let's not go with that. Okay, let's have a look at how to do this now. Okay, so we import TensorFlow as TF, and from TensorFlow, this is important, from TensorFlow we're importing Keras. Okay, sequential, dense activation input layer, great. Here's the model we looked at earlier. And yeah, an important thing to notice is this is an object. So it's got a lot of methods associated with it. Many methods, in fact, including model.predict. So you can, of course, do predictions here. One nice thing about Google Colab is it automatically pops up these things so that you can read the documentation straight from the browser like that. Okay, model.summary. This is a useful way to summarize your model as suggested. Number of parameters per layer and number of parameters in total. Number of neurons here per layer. Okay, great. Anything else? No, I think that's good. And yeah, neural networks have huge numbers of parameters, so almost 5,000 just with 2 hidden layers and 64 neurons per layer. Okay, so now we compile the model, associating the loss and optimizer with it, and also some metrics. So, metrics are just how are we going to assess our model, and we're going to use accuracy. Accuracy is in general not a great way actually to assess how well your model is performing. But just for simplicity, we use it here. And accuracy is just the proportion of correct classifications in this case. Let's just generate some random data from a normal distribution. So we're going to fit the model on some random data. So of course we don't expect our model to learn. We're going to do a classification task with 3 outputs. So we're trying to classify between 3 outputs, and we have 9 inputs that we're passing in. So actually, if we have a look at this data, so xtrain, here's a matrix, and matrix has shape 509. So 9 input variables, 500 examples of these input variables, and we're mapping to 3 classes. Also randomly generated, 0, 1, and 2. These are the class names. We want to one-hot encode them. So from keras.utils, we import 2 categorical. This just one-hot encodes it. One-hot encoding means that this 2 is going to be the number 2 position. So 0, 1, and 2. 1 is going to be mapped to this 1 here. And 0 is going to be mapped to the 0th position. So you can see how this vector is going to be transformed into a matrix. There are advantages for doing that, but it's also required for the loss function that we're using, which is categorical cross entropy. We specified it right here, compile. Okay, let's do model.fit. This is going to train the model. This is what you'll see when you're training a model. So we actually have quite a high validation accuracy. It really depends. Like as the average should be 0.333 because of course it's completely random data and your model's going to get it right a third of the time because it's just completely random. Also note that the in-sample accuracy given here as accuracy is tending to 1. This is because your model's overfitting and it's learning from that data and it's going to fit perfectly on this in-sample data, and you can see that here. And the orange is the validation, so it will hover around 0.33. Okay, so if you want to use your model to make predictions, model.predict, as we talked about, this is the across the 3 classes. So if you want to get an actual class label, we just take the argmax of each one of these. So it looks like this is the greatest number out of this row, and so the output is 1. And as you can see, if we do predict classes, then it does map to 1. Evaluate, this measures the accuracy. So let's try it. It should be 0.36. This should be about, yep, should be the last epoch here because we're evaluating on the validation data, which was being evaluated as the model is training here. So, okay, now we can have a little case study. Let me first see if there's anything that I'm missing here. Maybe I'll just go over some important slides. Often you'll deal with poorly distributed class data. And this is a way to fix it. You basically pass into the model saying, okay, I recognize that the 95% of my data lies in class 0 and only 5% in class 1. So please treat this accordingly. That's how you pass it into the model, and you pass it as a dictionary, with each class being mapped to the probability of a random input or a random output lying in that class. If you don't deal with this problem, your model will just predict the class that has more examples in. If it's like class A has 95% of the data, your model will just predict class A for everything and still get 95% accuracy. Okay, yeah, this is just a summary. Like, this is the entire Keras model right here, including compiling and fitting and evaluating. Okay, so let's try this California housing prices. This is nice because with Google Colab, it comes in the sample folder. So this is also here, and it's got the MNIST. So what are we doing? Okay, we're trying to predict the house value of a given house in California, given the longitude, latitude, and some other variables. One thing I wanted to try is projecting the longitude and latitude onto a projection space, or like a 2D space, like a map. What my hypothesis was that a neural network would find this easier to learn rather than longitude, latitude. And I just wanted to do it because I guess this is interesting. So yeah, here we're just projecting this longitude, latitude space onto this 2D coordinate space. and we then save that back into the model. So now, or not the model, the data frame. So now we do in fact have these coordinates and no more longitude, latitude. All right, let's first build a model, a linear regression model with stats models to have some kind of threshold to beat. This is not a course in stats models, so we're going to skim over details, but essentially endogenous variable is median house price. Exogenous is all the other variables apart from median house price, and we're adding a constant, of course, so we can have an intercept. All of the variables end up having or being significant at the 5% level and even at the 2.5% level. If we make some predictions, we see that the MAPE, or mean absolute percentage error, out of sample, so data this model hasn't seen, is 29.73. Okay, let's see if we can beat that. So deep learning, always normalize your input features. So normalizing, subtracting the mean and dividing by the standard deviation. So we've transformed this x data into a normalized x data using scikit-learn's standard scalar. Okay, now let's build a model as we've seen in the slides. So here we're just trying 128 neurons per layer, 2 hidden layers. Activation function is ReLU, and no activation function on the output, and a single neuron. Why? Okay, this is a regression task. We're predicting one output, and it's unbounded. Ideally, I mean, actually we can add a ReLU because we're only trying to predict positive outputs, so it shouldn't make a difference. Okay, loss function mean squared error because it's regression. Optimizer, RMS prop, we'll talk more about optimizers soon. This callback thing, let me go back to this. Callback, so what we're doing is if the validation or out of sample loss increases 5 times in a row, then we stop training. This is called early stopping. So here you can see it training. And this will go on for a little while, but let's just skip ahead. Okay, so like I said, when you have this history, we're saving to history NN, history neural network, that denotes. We can actually put this in a pandas data frame because history nn.history is just a dictionary of each one of the metrics and these metrics evaluated over time. So you can make a pandas data frame using a dictionary, of course, where the key is the column name. So if we just select the mean squared error and the validation mean squared error and plot this, this is what it looks like. Very nice and smooth, converging pretty quickly. So if we make predictions out of sample, we see that we get like under 27, which is a small improvement, not significant at all, but a small improvement on the linear model. So let's now try to improve the neural network. Okay, so there's a lot of hyperparameters meaning that you can't learn the parameters. There's a lot of hyperparameters associated with a neural network, right? We've got the number of hidden layers, the number of neurons per layer, the activation function, the initialisation logic we'll talk about, and all of these things. Okay, so one way is just by systematically doing a grid search. Of course, huge computationally. You could also do a randomized search, also huge computationally. There are some other ways and even some reinforcement learning based ways to do this better, but we're not going to talk about that because we want to build intuition in this course, much more important at this stage. All right, number of hidden layers. This is a great way to increase the complexity of your model. If your model is learning, but it can go further, then you can add more hidden layers. Or you can add more neurons per layer. In general, it's better to add more hidden layers just from research and from experience, this tends to make more sense, and it just tends to be better. And also, as you can see here, I've noted that due to parameter efficiency, it's better. Also note this stretch branch approach. What you could do is build a huge model and then regularize the model enough until it fits well. But I don't do this often, and it's not very, yeah, you don't see that approach too often. A way to determine the learning rates, this is how fast your model is trying to learn, is to start with a large learning rate, incrementally decrease it, and then once your model is just at the point where it diverges, then divide by 3, and keep on doing that until the model no longer diverges. Okay, skip over a lot of this because we've run out of time already. Okay, vanishing exploding gradients, huge problem. We've talked about the sigmoid activation function. It tends to saturate at 0 and 1, and then this ends up with almost 0 gradients. So this is actually the problem. It's the sigmoid activation function itself. So you could replace it with the ReLU. And also the weights initialization. We'll talk about that in a second. So one way to solve this is with this Glorot and He, sorry, I'm probably butchering that, initialization. What this does is it ensures that there's less of this, I'm not going to go too much into the theory, but there's equal variance across the neurons, or the weights in the neurons across the layers. So this is a good initialization technique, but we're going to focus a bit more on the Lacoon and the SELU combination. So if you wanted to change the initialization, what you do is you pass in this kernel initializer and you set it to whatever you want. So let's see how to do this. Kernel initializer, and we set it here. So you could also have like this. Note these don't have to be the same between layers, but in general, I think most of the time it's better to have them the same. Okay. So non-saturating activation function. So we've talked about that. The model might not be able to learn with a sigmoid activation function because of this 0 gradient problem. So the ReLU activation function doesn't have this problem. However, you get this thing called dying ReLUs where the neurons just output 0 all the time, and that's not useful either. So the leaky ReLU addresses this problem because it has a non-zero gradient everywhere. However, LU is actually slightly better. And this is the formula for the LU. And this is what it looks like. So LU is in blue here. ReLU is here, and then leaky ReLU is here. So why does the LU help? Okay, well, it helps the vanishing gradient problem as it has a mean closer to 0 for outputs less than 0. Okay, so SELU or scaled LU has been shown to do self-normalizing, and what this means is, well, it is essentially making it easier for the model to learn when you normalize, and this self-normalizing feature means that you the model normalizes itself using the SELU along with the Lacoon normal initializer, which is why I said we're going to focus on these. Okay. So key takeaway: using the SELU activation with the LeCun normal kernel initializer is a great way for your to set yourself up for success with this model. Gradient clipping, let's not talk about that. Okay, choice of optimizer. So we've talked about descending this loss surface to find the minimum error to increase your accuracy and find the optimum weights. If you think about trying to find this minimum, you can imagine a ball rolling down a hill. So this is the idea of momentum. Then we have some other tricks to increase the performance. Here's some initializers. So yeah, momentum optimizer, like I said, a ball rolling down a hill. So here's an example of momentum optimization Keras. And his Nesterov accelerated gradient is almost always a fast and simple momentum-based optimizer. Adagrad, another optimizer. RMS prop, another optimizer. All of these optimizers are great, but we're going to focus on Adam. So Adam is using a combination of benefits from all the other optimizers. And it's a very famous one. And it's just called Adam in the Keras optimizer, so you can just call it like this. However, Nadam is probably the best version, and it's using Adam, but what it's doing is instead of descending the gradient and evaluating the gradient at each point along the way, what it does is when it wants to descend this loss surface, it peaks a little bit ahead and calculates the gradient at this point. And it, in my experience, outperforms Adam a lot of the time. Okay, so in general, Nadam is the best. Let's have a look at this. Okay, non-saturating. Okay, so here we define the LU activation function. And as you can see, there's none of the saturating at 1 and 0. And if we're using the LU compared to the ReLU, you can see that they have a very similar shape. This is expected. But note that at 0, the ReLU has a 0 gradient, whereas the LU has a non-zero gradient. And so we can still learn a lot of the time, where ReLU, you'll have an issue with these dying ReLUs. Okay, with the self-normalizing model, here is a link. You can find this in the notebook, of course. So LeCun normal with the SELU activation. Okay, comparing optimizers. This is a cool little exercise. I'll have this running in the background because it takes a minute or two. Okay, regularization. Regularization is just essentially trying to stop overfitting, where your model learns everything that it can about the training data, but it learns so much on the training data that it can't generalize to out of sample data. And what you want to do is you want to maximize the accuracy on the out of sample data. But you can't give the model the out of sample data because then it cheats and learns in sample, right? So here are some examples of regularization. Dropout's probably the coolest and the best one. Monte Carlo dropout, actually even cooler, but this is a whole other topic. So L1 and L2, these are very famous regularization techniques. You just add a kernel regularizer like this into each hidden layer that you want it to act on. Dropout, what it does is each one of the neurons, or a Bernoulli distribution is applied to each one of the neurons with a certain probability, 0.5 usually, and a Bernoulli 0 and 1, right? That's what it maps to. So at each training instance, randomly, some of the neurons are going to be set to 0, and so they're going to turn completely off. There's a nice diagram here. So randomly at each interval, a neuron turns off. Sometimes it's this one, sometimes it's that one. It's random, so it's going to randomly turn the neurons off. Of course, this means your neural network's on average half the size. In order to implement dropout, you just add a dropout layer in between each layer here. So there's a dropout layer for the hidden layer, there's a dropout layer for the first, or sorry, a dropout layer for the input layer, and one for the first hidden layer, one for the second hidden layer. And of course you don't want to drop out your outputs. What this is doing is it's reducing the chance that your neural network learns through one specific path. So maybe all the information starts flowing in one specific path, but what you want to do is you want to make sure that your model is not doing this, because it's going to overfit in that case. That's the intuition. Also, you want to multiply each neuron's input connection by 1 minus the key probability after training. Input connection weight, sorry, because your neural network is going to be smaller on average. Okay, Monte Carlo dropout. I'm going to make a whole separate video on this, so let's keep that for later. Okay, so let's look at optimizers that we're running in the background. So what I've done here is, using the California housing data, I've plotted the in-sample loss and out-of-sample loss for each of the optimizers. So as you can see, Adograd tends to learn the slowest, and here it performs terribly out-of-sample. But as expected in theory and in practice, NADM outperforms all the optimizers, reaching convergence very quickly, like after 10 epochs. And here we just show how to actually do this dropout. Like I said, very simple, in between each layer, adding this dropout, and you can set the rate. 0.5 is normally a good starting point. Okay, now we've talked about a lot, but now what we're going to do is we're going to give you some practical guidelines. So when you go into a new model for a new task, what do you want to do? Okay, this is like my standard default layout. This is also the one recommended in Geron's book, the one where I got this from. Yeah, super awesome layout, and this works most of the time. I highly recommend you start like this. So you use the LeCun normal initialization with the SELU. Okay, why do we do that? Remember, self-normalizing is going to help your neural network learn faster and better, reach a more stable gradient, or a more stable minimum in the error surface. Normalization, we don't need to normalize. Like I said, we have self-normalization from this. Regularization, okay, so you can start with early stopping, where you stop training once your out-of-sample loss starts to diverge or increase. If this is insufficient, that's when you can add in dropout. And optimizer, of course, NADM, we've seen practically that it works as well. Things to note, always standardize your input features. Yeah, never don't do that, because if you think about the loss surface, you want this thing to be as smooth as possible for your model to learn. So if you don't standardize your input features, you end up having some inputs that are very large, like you saw in the California housing prices. The coordinates are very large, like in the hundreds of thousands or something. And some inputs are very small. And so you have this very stretched out looking loss surface, which is going to be hard to optimize on. If you imagine rolling a ball down this very long surface, it's going to be hard to find the bottom. Whereas if you standardize, make it into a nice unit bowl or something, it will find the minimum very quickly. And drop out again for regularization. If you have a custom model that can't self-normalize, remember, self-normalizing only works on the standard sequential fully connected neural network. If you're using a more custom model, you can't self-normalize, then you should do LeLU, and if possible, batch normalization. So we sort of skipped over batch normalization, but this is something that you can look at in your own time. But in general, for a standard model, you don't need that. Okay, is there anything else to touch on here? No, here I just showed that this model, using some of the guidelines that I've just talked about, so we're increasing the neurons and number of layers. We're also using this self-normalizing. We run this on the California housing data, using NADM as the optimizer, early stopping, just like I've laid out in the guidelines here. We end up seeing that the MAPE is 23.53, which is a huge improvement on the previous neural network of 27, I think it was. So, of course, you can improve this much further. Feature engineering is going to be super important, but since this is just about neural networks, we're not going to cover that. Yeah, so that's actually everything, like the summary of, yeah, I mean, that's the whole course right there. The main takeaway is this slide, but also please visit this notebook and just work through it in your own time. See if you can code up some of these optimizers and if you can code up some of these activation functions, just some simple tasks, and then just get building your own neural network straight away. Start by trying to beat my score in the California housing data. I'm sure you can do it. MAPE of 23.53 or less out of sample using their test set. And yeah, thanks for watching. Please leave some feedback. We're looking to do a lot more of these types of videos in the future. If you have any requests for anything that you want to cover, let's say that you want us to cover Monte Carlo dropout, then leave a comment. Thanks for watching. Bye.